All right. In this example, we have V1 is 1 I hat, negative 3 J hat, and 2 K hat. And then we have V2 is negative 2 I hat, 2 K hat, J hat, sorry, and negative 5 K hat. And we want to compute V1 cross V2. We're going to compute the cross product here. To do this, I usually like to set it up using the matrix formation with a determinant. So I have I, J, and K across the top, and then each of the components, 1, negative 3, and 2 for V1, and V2 is negative 2, 2, and 5. Okay, and then to compute the cross product, we work along the top row, the first row here. And so we have I hat, and then imagine if you close out this row and this column, then the little submatrix that you see right here, negative 3, 2, and then 2 and 5. So that should be a negative 5, is the first one. Okay, and then alternating signs, we get minus J hat. And then, so if I close out the first row again, and this first or second column here, I have 1 and negative 5, then 2 and negative 2 is that. And then switching signs again, K hat along the first row. Again, I'm holding this first row constant, and I'm holding this first or third column here constant. And so I have this little submatrix here, 1, negative 3, negative 2, 2. Okay. And now you take the determinant of each of these 2 by 2s. And so you go in the I hat direction. I have negative 3 times negative 5, which is positive 15, minus 2 times 2, which is 4, minus J hat. 1 times negative 5 is negative 5, minus 2 times a negative 2 is a positive 4, plus K hat. I have 1 times 2, and then minus a negative 3 times a negative 2 makes a minus 6. So last but not least, then I'm left with 14, or sorry, 15 minus 4 is 11 I hat. Let's see, minus, we have a negative 4, or sorry, negative 5 plus 1. 4 is a negative 1. Minus that makes it a plus J hat. And then plus, actually it's going to be minus, we have 2 minus 4, 2 minus 6, which is negative 4 K hat, which is then, of course, our resulting product, cross product, which would be the vector that is normal to V1 and V2. Okay, I hope that was helpful, and I'll see you in the next video. All right, this is example 2. And so in this example, we wanted to prove that the cross product is distributed across a sum so that we can write that U cross the sum of V plus W is the same thing as U cross V plus U cross W. So this proof, we won't go through the whole thing. I'm going to leave this as an exercise for in class. But what I will suggest is kind of a sketch of how to go about proving it. And so we kind of want to treat this as like two things and show that the two things are equal. So you have the left-hand side, which is U cross V1 plus VW, or not V1, sorry, V plus W. Okay, and then on the right-hand side, you have the two U cross V, that's a V, and then you have U cross W. So what I would suggest doing is doing this component-wise and then kind of at the end, compare and see if these two things actually turn out to be equivalent. Okay, so if they are equal, then that shows that the original equation holds. So imagine that you let U equal U1, U2, and U3. You let V equal V1, V2, and V3, and then W equal to W1, W2, W3. Now, you can extend this into, I was writing this as an ordered pair, but this is in fact a vector notation as well. So you could extend this to n-dimensional space, just adding on more components to the result would still hold. However, since we're dealing with a cross product, we're referring to three-dimensional processes only. The cross product isn't defined higher dimensions. Okay. So then what I would suggest doing is on the left-hand side is adding these two together component-wise, and then in the resulting cross product, you would have in the I hat U1 and then V1 plus W1, J hat U2, V2 plus W2, and then K hat U3, V3 plus W3. Okay, and then compute that out, and then simultaneously over here, compute the cross product of I, J hat, and K hat of U1, U2, U3, and V1, V2, and V3. And then also the I hat and J hat and K hat of U1, U2, U3 with W1, W2, and W3. Okay, so compute these two quantities out and then add these quantities together, and that would be then the comparison that we would need to make here to see if in fact this equality holds. Okay, so here what we did on the left-hand side, we added these two vectors first, and then we took the cross product. On this side, we're taking the cross product of u and v and u and w first, and then adding those components together. If we compare those sums at the end, then we're going to see we have to determine if in fact they are equivalent. If they are equivalent component-wise, then this equation holds, and that's what you'll need to do to prove this in class. Right? I hope that was helpful, and I'll see you in the next video. All right. In this example, what we're looking for is we're given 3 points, P, Q, and R. They are non-collinear, that is given, and we want to determine a unit vector which lies normal to the plane. Okay. So we have to figure out what is the normal and then make that a unit vector. So that's our primary goal for the situation. So in doing this, since these 3 points are non-collinear, choose any two. I usually just take P and the first point, which is P in this case, and go to Q and then P to R. And those form my two vectors. And so we form those two vectors by subtracting component-wise. So 2 take away -2 gives me 4. 1 take away -1. Oh, this is a -1, and this is, oh, that's a -1. That looks funny. There we go. -1 take away -1, that gives me 0. And what else do we have? 1 take away 0 gives me 1. Okay, so there's my vector PQ, and then PR is going to be the same thing. 2 take away -2, so that's going to give me, looks like a 4 again. 2 take away -1 gives me a 3, and then a 2 take away 0 gives me 2. Okay, all right, so those are my two vectors, PQ and PR. And so now I'm going to compute the cross product between these two vectors, and that will give me then the normal vector. So I'm going to compute PQ cross PR. If I plug those into component-wise and take the determinant, I get that the normal vector, this is going to be my normal vector, is going to be equal to -3 I hat minus 4 j hat plus 12 k hat. Okay, so I'm plugging this into the cross product and taking that. I've already done that, so this is the result of this. So now I have that this is my vector, my normal vector, and now I wanted a unit normal vector, which means I need to normalize this vector n. Okay, so n, I'm going to make my unit vector is going to be n divided by the magnitude of n. Okay, and so to do that, I can simply take the dot product of n with itself, and then divide by that value, and then multiply that by n. So this is going to be the square root of n dotted with n times n. That's going to be my, so the n dotted with n is going to give me 9 plus 16. Let's see. So let's see here. So n dotted with n is going to give me 9 plus 16 plus 144. what is that? That's 6, 10, carry 1, that's 4, 5, 6, so 160 plus 9 more, so that's going to be 169. And then the square root of that then, okay, is dot n is equal to 13. All right. Well, that turns out to be a nice number. Okay, so it's a perfect square. And so then we have 1 over 13 times -3, -4, and 12. Okay, and so this would be then the unit vector u that is perpendicular to the plane, but is also a unit in length. I hope that was helpful. And yeah, I'll see you in the next video. All right, in this video, what we're looking for is to determine the area of the parallelogram, or sorry, the area of the triangle that's formed by these three vectors. So these are the three coordinates that make up the vertices of the triangle. And so, since this is a triangle in the plane, we can determine like in the last problem, we can determine the normal vector to these and then take the magnitude of that uh, resulting vector. And that actually gives us then an area of a parallelogram. And then if we take half of that, that'll give us the area of the um, triangle. Okay. All right. So let's go ahead and do just exactly like we did in the last one. So I'm going to create the vectors PQ and PR. Okay. Uh, just like in the last one, I'm going to subtract those. I think I originally did it with QP and QR. It doesn't change anything other than the direction, but so it'll still be the same. Just uh, since I already solved it this way, I'll do it this way. So Q minus P, sorry, minus Q. That's going to give me -1, -2, and 1. And then let's see, we have -1 minus 2 gives me a -3. 1 minus 1 gives me 0, and 2 minus a -1 gives me a +3. Okay. All right, so those are my two vectors, QP and QR. And from this point, and you notice you would get the exact same result if you do, the vectors will just be pointing in a different direction. But since we're looking at magnitude for area, it's not going to change anything. So let's look then at the cross product of Q, that's a P. Wow, QP cross QR. Okay, so if we look at the cross product here, we get, looks like -6 in the I hat minus 0 and 6 negative in the K hat. Okay, so that is the unit, not the unit, sorry, that is the normal vector. If we divided by the magnitude of it, that would give us the n hat like we did in the last example. But instead, what we're going to do is take the magnitude of this. So we need to compute that. And so we're going to take, if we call this the normal vector, then we're just like in the last one, we're going to take n, dot it with n. And so we're going to get, and then take the square root of that because we need the magnitude. And so we have the square root of -6 times -6 is 36 plus 36 and 0 plus 0. So there's just these two terms. Okay, notice that 36 is a perfect square, so I can actually factor that out. That's 36, and then I have a 1 plus 1 inside. So I'm factoring a 36 out. And the reason why I'm doing that is because I know 36 is a perfect square. And then 1 plus 1 is just 2. So I can write this as the square root of 36 times the square root of 2. Square root of 36 is just a nice number. It's 6. And so this becomes simplifying. This becomes the square root of 36, which is 6 square roots of 2. So now this is the area of the parallelogram that is spawned by these two vectors, Q and P. So the triangle then would be half of this total area. So the area of the triangle, in other words, this isn't exactly it, but this is the area that we found is all this. And the area of the triangle that we're looking for is this one right here. So we're just going to divide this area. Oh, sorry. We're just going to divide this area, and that'll give us the area that we're looking for, which is this region right there. Okay, so the area of this triangle then is the area is going to equal 3 square roots of 2. Okay, all right, I hope that was helpful, and I will see you in the next video. All right, this is just an extension of example 4, just to kind of give a little bit more of a visual cue for this problem and to verify, make it a little bit more maybe palpable or understandable. So I'm going to first put in the 3 points here in GeoGebra. I have this set up in Algebra View with the three-dimensional viewer in the classic format, and then Q is equal to 2, 1, -1. You can see the points thrown up on the right side of the screen there, and then R is -1, 1, and 2. All right, so let's make the vectors. So this is going to be QP, so a vector from Q to P. There it is, and then a vector from Q to R. There they are. Okay, and now I'm going to take the cross product across U comma V. And so you can see the vectors showing up here. You can kind of get a sense. So there's the plane that is spanned, if you can imagine seeing P, Q, and R there. And the normal vector there is coming, is pointing from the origin out, but that's the normal vector. So if you can imagine extending that thing to the plane, that would be the normal vector there. Remember, vectors are coordinate free. As long as they're saying magnitude and direction, you can move them around anywhere in the space in their equivalent form. All right, so let's look at first the triangle. So let's make a polygon. With those 3 points. So P, Q, and R. So there is the polygon, and you'll notice that the polygon gives us this value. And what is that value? That's the value of the area of that triangle. So you can see the triangle there, and then you can also definitely see better, I hope, the fact that this is the normal to that. Okay. All right, so let's find out the magnitude of the normal vector and compare it to the area here, numerically, of the polygon, of the triangle that we were talking about. Okay. All right, so we're going to look at the square root. The vector that is normal was W. That's this vector here. And we want the dot product of W with W, which is exactly that. Okay. So A is the value of the area of the parallelogram. And so now if we take A divided by 2, because area of a triangle is half base times height, we get 4.23 and 4.23. So those are exactly equal, where they've evaluated the square root of 2 being 0.41, blah, 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 blah. Okay. All right. So I hope that gives you a little bit more geometric intuition as to what we're saying. If you can imagine extending a vector out from Q over to here, then the parallelogram you could see is extended from there. And then what we would do is calculate, and what we calculated with the magnitude of W, or well, W, but the value of A here is the area of that entire parallelogram. And so half of this, then the triangle you see here is the area that we were investigating. Okay. All right. I hope that gives you a little bit more geometric interpretation and a little bit more value in that example. And I'll look forward to seeing you in the next video. All right, in this example, we're going to look for the volume of this. We're looking for the volume of the parallelepiped. Parallelepiped. It looks like parallel piped, but we usually say parallel. I forgot an E. Parallelepiped. And so we're looking for in other words, we're looking for the area of the box that is spanned by these 3 vectors. Okay. So from the box product, the lemma and the notes, what we see is that the resulting volume can be found by taking the cross product of 2 of the vectors and then dotting that result with the remaining vector. It is arbitrary, your choice of how or what order you choose to do them in. So if you chose to do V3 cross V2 and dot it with V1, or V2 cross V1 dotted with V3, or V3 dot cross V1 dotted with V2, the result would be exactly the same. The only difference is that the geometry in the intermediate steps would represent different quantities or different values, primarily in the sense that the cross product is antisymmetric. So your normal would be pointing either opposite direction of the surface that you're trying to construct. So that would be just the only thing to consider there. So given that that is arbitrary, how we choose to, let's look at computing the volume of V2 cross V3, and then we'll dot that with V1. Okay, so that's how we will challenge our challenge ourselves, I guess, to this problem. Okay. All right. So if we take V2 cross V3, the result of this cross product yields the vector 7 in the I hat, a -3 in the J hat, and a -4 in the K hat direction. Now I want to take this and dot it with the V1 here. So this is, I would call it my normal vector. So I'm going to dot my normal vector with V1. And so I get 7, -3, -4, dotted with 1, and -3, and 2. And so when I do that dot product, I get that this result is 8. Okay. And then the magnitude of this is the last part. So I want to take the square root of this magnitude. I guess it should be stated that these are in magnitude. This is equal to the volume. That's what the box product is saying in lemma in the notes there. Okay. And so the magnitude of this is, of course, the absolute value of this, which is the square root of this thing, which is obviously 8. Okay. So that is the volume of this particular parallelepiped. I hope that that was helpful, and I will see you in the next. All right. So it looks like we're drawing the same problem, but it's a little bit different, but it's exactly the same. So again, we're going to look for the volume, which we saw in the last video. We know the volume of this parallelepiped is indeed 8. But this time, we want to show a way of calculating that box product in a more direct manner instead of calculating both the cross product and the dot product, doing it sort of in one step. So this is what the um, lemma is specifically saying. So again, the order doesn't matter, but you take the cross product and then you dot it. This has the same form as the magnitude of you looking at the component wise, in our case, U1, U2, U3, W1, W2, W3, and then V1, V2, V3. So if you compute this determinant, then that's the same exact process as doing first the cross product and then the dot product. Okay. All right. So if I'll erase this for the room and we'll plug it in and see and verify that it does give us, in fact, the exact same thing. So we have -2 to -5. We have 1, 1, 1. And we have 1, -3, 2. Okay. All right. So if we compute this, we get -2 times 5 minus 2 times 1 minus 5 times -4. Okay. And simplifying that, this is -10 minus, it's like 2, so 12 plus 20. So -12 plus 20 gives us absolute value of 8, which is indeed 8. Okay. And if you're wondering where did these numbers come from, -2 is like the I hat in the determinant of the cross product. So this is like my I hat. This is like my J hat. Why is it minus? Because when you're taking the determinant, you alternate signs. So this is -2. It should be a positive, but there's a -2 here. This is a positive 2, but the switching the sign makes that a negative. And then this is a positive again, but because this coefficient here is -5, that's where that's coming from. And this is the result of the sum of the 2 times 1 minus 1 times 3, which gives us the 5 there. Okay. All right. I hope that that's helpful, and I will see you in the next video.